So in this video, we're going to look at a specific probability distribution called the binomial distribution. So if we let x be a random variable, then we say x follows a binomial distribution, which is written like this. I'll explain this in a second. So this sort of twiddle in the middle means follows. X is our random variable, and B, that stands for binomial distribution. So this just says the probability distribution x has is a binomial distribution. N is the number of trials, and we'll say a bit more about that in a second. And P is the probability of success. So you can only apply this to certain kinds of random variables. In particular, you need it to be something where there are only two possible outcomes, success or failure. So a binomial distribution is appropriate if, firstly, there are only two outcomes, success or failure, or it could be something like heads or tails if you're tossing a coin, but there can only be two possible outcomes. There are a fixed number of trials. So for example, you only toss the coin 10 times. And the probability of success, so P has to be constant. P can't change. So P is constant, and the trials have to be independent. So that means just that, for example, the first trial can't have an effect on the outcome of the second trial. So these are the conditions that have to be met in order to use a binomial distribution. If you're asked in the exam whether binomial distribution is appropriate or why it's appropriate to use a binomial distribution, then the answer is likely to be a combination of these reasons. However, just something important is that in the exam, any question where your answer involves these reasons, you must link to the context that's given in the question. So it's not enough to just parrot these reasons. You have to also link it to the context. Must link to context in question. So for example, if the random variable is the number of sixes someone rolls on a die, which follows a binomial distribution because the two outcomes are 6 or not 6. If we do that, say 5 times, there are a fixed number of trials, P is constant, the trials are independent, so it's okay. But if we're asked why a binomial distribution is appropriate, we would need to link each of these explicitly to this die that's being rolled 5 times. You just need to make sure you link because you won't get the marks if you don't link your reasons to the context in the question. Okay, so I've mentioned a few examples already, but another example, we'll just write one down, and that is maybe an archer firing arrows at a target with constant probability of success, 0.3, and maybe they fire 10 arrows. So then if X is the number of arrows that hit the target, then we can say X follows a binomial distribution with 10 trials and probability of success 0.3. Now, generally speaking, in a question, they won't necessarily tell you what X is, like I've done here. You'll be asked to find something, but they won't necessarily give you the variable name. So then you'll sort of have to figure out for yourself. You have to make clear for yourself what you're going to what x is going to be, and you just have to be careful about notation, as we'll see when we do some examples. So so in order to work out probabilities, so in this case, if we wanted to work out the probability that x is 5, that this means the probability that precisely 5 of these 10 arrows hit the target. So the idea is we've got somebody who's, they're firing arrow. I don't really know how to draw a bow and arrow, but that's the wrong way around, isn't it? Never mind. So they're firing arrows at some sort of target, and maybe some hit the target, maybe some miss. And we want to work out of the 10, the probability that 5 of them hit the target. Okay, so we want 5 out of 10. Well, how could this happen? Let's just think the very first arrow can either hit or miss, can't it? Either hit or miss. This is the first arrow. The second arrow can also then either hit or miss. So there are a lot of different, so there are already 4 combinations that are possible. Out of the 10 arrows, we need 5 of them to hit the target. Now, how do we work out how many different ways that could happen? So it could be hit, 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 miss, 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 miss. Or it could be something jumbled up that's quite different. So it could be something like miss, hit, hit, miss, 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 hit, and so on. Miss, hit, hit. So that's another. So there are a lot of different possible combinations. How many are there? The answer, you might remember when we did the binomial expansion, n choose r. 10 choose 5, which is also written 10c5 like this, is the number of ways of choosing 5 things out of 10. So the number of different ways that 5 of the arrows could hit is going to have something to do with 10 choose 5. That's the number of different ways. So if we want to work out the probability x is 5, we're going to do 10 choose 5. That's the number. We're counting all the different ways it happens. And then we're going to multiply that by the probability of the 5 hits. So each of those happens with probability 0.3. They're all independent, so we can multiply them together. So we get 0.3 to the power of 5. And then the other 5 misses. Well, if the probability of a hit is 0.3, the probability of a miss is 0.7. So the probability of the 5 misses is 0.7 to the power of 5. And then we can work this out, and this will give us the answer. And remember, 10 choose 5, this just means 10 factorial over 5 factorial, 10 minus 5 factorial. But obviously your calculator also has a button for it. So if you just plug into your calculator, 10 choose 5 times 0.3 to the 5 times 0.7 to the power of 5, you should get 0.1029 to 4 decimal places, which is the right answer. Okay, so what we did here, everything we did here was quite complicated. The good news is there's now a much simpler way. So using the same kind of reasoning, we can say in general, so this is kind of important, in general, if x follows a binomial distribution with n trials and probability of success p, the probability that x equals r is n choose r times p to the r times 1 minus p to the n minus r. Okay, and we can see we got that in this example here. This is exactly the same as this. So that's why I say the same reasoning gives us this formula. So in the book, they just state this formula as if it's magic, but it comes from somewhere, and it comes from doing this reasoning that we did in this example. Right, so now let's see some examples. So the kind of questions you can be asked are, first of all, we'll just do a very simple one. If we're given that X follows a binomial distribution with 15 trials and probability of success 2/5, the question is find the probability that X is greater or equal than 14. Okay, so here there are 15 trials. So we're asking what's the probability there are at least 14 successes. So the only way there can be so there are two ways there could be at least 14 successes. Either there are 14 or there are 15. Obviously, there are a lot of different ways you can get 14, but that's counted by the formula, so we don't have to worry about that. Okay, so now let's just apply this formula with R is 14. And of course, N is 15, P is 2/5. So letting R be 14 in the formula, we have 15 choose 14 times 2/5 to the power 14. And then 1 minus P is 3/5, and N minus R is 1, 15 minus 14. So that's the probability X is 14. The probability X is 15, we'll now let R be 15. We get 15 choose 15 times 2/5 to the 15, and then it's times 3/5 to the 0. But anything to the power 0 is 1, so we don't have to worry about that. Okay, and then we can work this out. So now you just enter this information in your calculator, and you should get a very small number, 0.00003 to one significant, well, maybe let's give it to a few more. Let's say 0.252 to 3SF. So that's a very, very small probability that we get at least 14 successes. The kind of question more often you get in the exam is something where there's a bit more context. So if you're asked the following question, the probability a person in a group is left-handed is 12%. There are 30 people in the group, and then we've got part A. Find the probability that 6 of them are left-handed, and part B, find the probability fewer than 2 of them are left-handed. I don't actually know what the probability somebody's left-handed is, but I think 12% sounds reasonable. Or maybe I think it's slightly less than this, actually. Okay, so notice we're not told what X is here. You have to figure that out for yourself. But it's not too difficult because we're being asked to find the probability people are left-handed. So the first thing to write in your answer is let X be the number of people who are left-handed. It's really good practice to make clear what your random variable actually is, and to also say that it follows a binomial distribution with 30 trials, because there are 30 people, probability of success 0.12. So this stuff here that we've put is important. Okay, and then we want to find the probability that X is 6, the probability that 6 people are left-handed. So we can just use the formula, or you can use your calculator. So although we used the formula before, in fact, for this one, you can also use your calculator. Yeah, generally speaking, it's easier to use your calculator than to do all this working. So if you have, maybe at this point, pause the video and watch the explanation of how to do it on your calculator and then come back. So the probability x is 6. Well, if we, either using your calculator directly or using the formula is more work, but this is what you get if you use the formula. In general, I'm not suggesting it's good to use the formula because it'll slow you down, but anyway, we get 0.0825 to 4 decimal places. It's quite common in probability to give answers to 4 decimal places. Okay, so that's the answer to part A, and then part B, find the probability that fewer than 2. So the wording's quite important here. What does fewer than 2 mean? It means less than 2. So we want the probability x is less than 2. Now, we're talking about numbers of people here, and the binomial distribution is a discrete distribution. It can only take whole number values. So it couldn't be 1.5, and indeed here it wouldn't make sense to have 1.5 people. But it can be x is 0, or it can be 1. We're not interested in when it's 2, because this is a strict inequality. The reason it always makes sense to have whole number values is because r, in the probability x equals r, is the number of successes. So that has to be an integer that's at least 0. Okay, so again, you can either use your calculator or you can use the formula. It's, again, more work to use the formula, but none of them are left-handed. And then this is 30 times this. So there are some shortcuts that, if you're good at simplifying binomial coefficients. And in this case, we get an answer of 0.1100 to 4 decimal places. So chance that fewer than 2 of them are left-handed is about 11%. Okay, and that concludes this video.